Hello guys, today we're going to be talking about how to measure an unknown inductance and an unknown capacitance using a couple of simple circuits, an oscilloscope and a function generator. The circuit we're going to be used to measure capacitance is a simple low-pass filter circuit with a fixed resistor and an unknown capacitor here. In order to understand how we're going to get capacitance from this, we need to derive its transfer function. If you express the output voltage VO in terms of the input voltage VS, V source, we can use the potential divider equation where ZC is the impedance of the capacitor here and R is the resistance of this fixed resistor here. If we let the source voltage equal a signal e to the power of st, this could be a e to the st where a is the amplitude of the signal. I've said amplitude is 1 to make things simple. And then we look at the defining equation for the current through a capacitor, capacitance times by the differential of voltage with respect to time. Substitute this source voltage into dV by dt. We end up with S times C e to the power of st, or CS times Vs, because Vs equals e to the st. Then if we rearrange this to get impedance, because IC equals CS Vs, get Vs over IC, which equals 1 over SC, then we can substitute this back into our potential divider equation here to get this equation here, and then we rearrange that to get our voltage gain in terms of Laplace's variable S, and this is our transfer function here. Now if we remember the standard form for the first order transfer function, 1 over 1 plus time constant times Laplace's variable, we can compare these two to get the time constant equals RC, where R is our fixed resistor resistance and C is our unknown capacitance here. So it's all about measuring what the time constant is using our oscilloscope. Now if we look at the voltage against time curve for a charging capacitor, it looks something like this. It has this equation, V final minus V final e to the minus t over RC. Now we've already established that our time constant is RC, so if we let t equal RC, we end up with this equation here, VF minus VF over E, which simplifies to 0.63 times VF, or 63% of VF. So if we measure the point where V equals 63% of the final voltage, and then read the time that that occurs, that will be our time constant, and that will be equal to RC, so we find C from that. In order to measure our unknown inductance, we're going to be using an LC tank circuit or an LC resonator circuit, and we're going to be sending a square pulse through it. And you'll notice that every time there's a pulse, the circuit's going to resonate and it's going to be underdamped like this. Now the damped's natural frequency is equal to 1 over the square root of LC, and this is because the resonant frequency occurs when the inductive reactance and capacitive reactance are equal. So we get omega L equals 1 over omega C, and that just simplifies to omega equals 1 over LC. Now omega is in radians per second, but of course we just divide that by 2 pi to get it in hertz. So here we have our 1 kilohertz square wave with an amplitude of 1 volt passing through the low pass filter circuit, and we're going to try and measure the capacitance in there. So let's start by zooming in on one wave here, adjusting its position, and we're going to use cursors to track where the time constant is. Let's adjust the cursor here to the top of the wave. Switch cursors, adjust this one to the bottom of the wave. And now you see the amplitude of this, the voltage amplitude is about 1 volt, which is expected because that's what's coming out of my function generator. So 63% of that is 630 millivolts. Let's adjust the second cursor until we reach 630, which is roughly there. So here we're getting a time constant of 980 microseconds. Let's put that into my calculator. What's that? 980. 980 times 10 to the minus divided by 2 kilo ohms. That was our resistor we used in the filter. And here we get 490 nanofarads, which is quite a bit more than what it actually says. And that's either due to errors in my calculation of the time constant or the tolerance of the capacitor. So here we're looking at one ring produced by the LC tank circuit, and we're going to need to measure its frequency in order to determine the unknown inductance. So again, we're going to use cursors, switch that to time, then we'll alter the system measure one period, and see here it says 1 over dt is 270 kilohertz, so let's plug that into our formula. So we get 1 over 2 pi times 270 kilohertz squared over the known capacitance, which I chose 1 nanofarad. That's 1 times 10 to the minus 9. And here it says that's 374 microhenries. Sorry, 347 microhenries, and the actual value of this inductor is 331 microhenries, so it's a little bit more, but not too far out.